Hi, my name is Peter Wilder. I am an HVACR drives application engineer at ABB. In this self-paced lab, I'm going to cover with you how to set up the ACH580 drive to operate a cooling tower. We're going to cover and practice how to set up the control wiring on the drive and also how to program the drive for the cooling tower application. The goals of this presentation are to teach you, as I mentioned just a second ago, how to program the ACH580 drive and where to land control wiring on the drive. We're going to do this through a series of step-by-step interactive labs. The labs will build on one another, so I do recommend that you go through the labs in order. And by the end of this presentation, you'll be more familiar with how to wire and program the ACH580 drive. This self-paced lab is made up of 6 sub-labs, and I just want to cover real quick what each of these sub-labs are going to teach us individually. First, in lab 1, we're going to learn how to enter the motor data into the drive and also how to set up the drive for hardwire run stop command and set up the drive to receive a vibration safety switch input from the tower. In lab 2, we're going to set up the drive to receive a temperature feedback signal directly into the drive and allow the drive to run autonomously off of that signal, what's called drive's internal PID loop. In lab 3, we're going to adjust the acceleration and deceleration times in the drive and also adjust the gain and integral times in the PID loop. In lab 4, we're going to cover how to set up the drive for BACnet MS network connection for monitoring purposes only. In lab 5, we're going to set up a relay output on the drive to be connected to a spray bar pump on the tower. This will allow the tower to operate a spray bar pump depending on the temperature of the feedback signal that the drive is receiving. And in lab 6, we're going to adjust the name of the drive. So instead of it just saying ACH580 on the drive's control panel screen on top, we could set it up to anything custom we want, such as Cooling Tower 2. In order to complete this lab, you will need a working drive. Now, on the pictures on the right, we have on the top a drive only, and on the bottom, we have a drive with a bypass demo unit that we offer. If you are using the drive with a bypass demo unit, you will want to set that up for drive only mode. Now, besides these 2 nice demo units, you could also just take a drive, powered off, for example, control power transformer on a workbench and connect it to a motor and wire up some switches for digital input control and maybe like a little analog potentiometer for speed control. That'll work just fine also. At the beginning of some of the labs, I'm going to ask you to land some control wires on the drive. For example, where's the run stop command going to be landed, or a speed reference. So I want to make sure that you understand on the drive here where the analog inputs go, which are in the green on top, the blue are digital inputs, the orange are digital outputs or relay outputs, and in the gray section at the very bottom, that is for serial communication, like RS-45, for example. So I just want to make sure that you're aware of this and also note some of the default settings for some of the inputs and outputs. It may make sense to reference this documentation when I ask you some questions about where to land some control wiring on the drive. Now, after I introduce each lab and the programming requirements that need to be done on the drive, I'm going to take a second and pause and allow you a chance to program the drive first before I show you how to do it so you can hopefully learn. Now, if you're a little lost in saying, where do I go? How do I start? I'm not familiar with the ACH580 drive. Here are 2 big hints. Most of the programming I will be doing in the drive is going to be done in primary settings and even a submenu of primary settings called Quick Setup. So if you're not familiar with these 2 features in a drive, I recommend that you watch these 2 videos first before going on with the labs. Now let's dive into lab 1. At the beginning of each lab, I'm going to introduce a configuration request, which is basically how I'm asking you to set up the drive or program the drive and wire it. Think of this as a customer asking you how to set up the drive for their application. In this lab, I'm going to ask you to set up the drive to receive a 0 to 10 volt speed reference to represent a 0 to 60 hertz speed signal on the drive. I'd also like you to wire up a hardwire run stop command to the drive and also wire up a vibration safety switch to the drive. I would like you to also program the drive to display words indicating that a vibration safety switch has tripped on the drive when the switch opens. We're also going to enter in the motor data into the drive. Now, for my demo unit, the motor data is here below at 0.33 horsepower, 0.8 amps, 1650 RPM, 230 volts, and 60 hertz. Your demo motor may have different information, and if that's the case, enter in that specific motor data for your demo unit. Now, to give you a second here to think about where to land control wiring on the drive, as I've asked you to do so, and also how to program the drive. Take a second, pause the video here, and I'm going to reveal where all the control wiring lands on the drive for this lab. All right, so here you can see I've landed my 0 to 10 volt speed signal on the drive on analog input 1 and analog input ground. And that's because the default function of AI1 is to receive a 0 to 10 volt speed reference. So no programming adjustments need to be made for this analog input to receive this 0 to 10 volt speed signal. Also, I've landed my run stop command on digital input 1. And why is that? Because DI1 by default is set up to receive a 0 to 10, hardwire run stop command. This again, if you reference back a couple slides, I showed you the default setup for inputs and outputs on this drive, and that makes it easy if you reference that to understand where to land some wiring to make your startup much faster. And the last item is the vibration safety switch. Again, digital input 4 is set up to as a safety input, normally closed. Now, the function of the name of it is called start interlock. So we will have to make some programming adjustments for it to indicate specific language such as a vibration safety switch. But the function of digital input 4 is normally closed safety. Now let's review the programming of the drive for Lab 1. Now to start with, to make my life easy to program the drive, I'm going to use primary settings. And I'm going to use the HVAC quick setup. Now, as I mentioned at the beginning or the previous slide, digital input 1 is pre-set up for hardwire run stop, and you can see that here under primary start stop. You can see DI in 1. So I don't have to make any adjustments, as I mentioned earlier, for this setting. For my speed reference, okay, analog input 1 by default is designed to receive a speed reference into the drive. Now, the scaling for analog input 1 by default is also 0 to 10 volts equals 0 to 60 hertz. So again, now I do not need to make any adjustments. Now, if you, for example, had a request to make your signal 4 to 20 milliamps instead of 0 to 10, you'd select the range here, okay, and make that adjustment as necessary. Also, you can adjust the range of what 0 volts equals as a scaled min and what 10 volts equals as a scaled max, if necessary. Now, if we go back out here, we go down to use safety interlock 1. By default, that's enabled. And that is digital input 4. DI4 high means that this input has to be high or closed in order to allow the drive to run. And that is, again, a default setting. So our safety circuit is connected to DI4. So that's all good. Now, we're asked to change the text on the screen, though. So right now, by default, if the circuit were to open, we would just see the word start interlock is open, which is pretty vague. We want to make that more descriptive. So here we're going to edit this, and we're going to select vibration switch. So now if the vibration switch opens on the drive, or DI4 opens, we're going to see the words vibration switch is preventing the drive from running instead of just the vague words start interlock. And that completes the first part here of Lab 1 for the programming. We're now going to cover next the entering in the motor data. To enter the motor data into the drive for Lab 1, I'm again going to start at primary settings. I'm going to navigate down to motor here. Select, and then I'm going to select nominal values. Now we're going to be asked some questions about the motor. So we have a single motor, and now we're going to enter in the information specific to the motor. Now here's a little trick. Don't hit next. You want to hit the arrow over button. And here we're entering the current, and for my motor, it's 0.8 amps. For your motor, if it's different amperage, enter in that specific motor's nameplate information. And speed here. Voltage is 230, that's already default, 60 hertz. And it is an induction motor, yep. And the horsepower here is 0.33. And we can disregard the cosine phi, that's optional. and also the torque. So now we can hit next. Now we're also being asked some information about the application. The minimum frequency is 0 Hertz. The maximum frequency is 60 Hertz. This is an area, if you wanted to set up a minimum frequency for the entire drive, which would apply to hand and auto mode. You could also do that here. But we're just leaving that alone at default, 0 to 60. And then it's going to ask us, are you about to exit the assistant? Do you want to save the settings? Yes, we do. So now we've programmed in the motor data into the drive. At the end of each lab, I'm going to show you the new modified parameters that would show up in the modified parameter list of the drive. For example, 20.47 start interlock 1 text now will show up in the modified parameter list of the drive. Also for reference, here's some screenshots of where I made some of the changes in the previous video for these specific settings. For reference, here's the motor data that will show up also in the modified parameter list. For Lab 2, we're now being asked to get rid of the 0 to 10 volt speed reference that's connected to the drive. Instead, replace it with a transducer feedback signal connected to the drive to represent the condenser water discharge temperature from the tower. We're going to use this to control the speed of the motor. When we're asked to do this, we're basically being asked to set up the drive's internal PID loop to control the motor speed. Now, the transducer that will be connected to the drive specifications are 32 to 212 degrees Fahrenheit is represented by a 0 to 10 volt signal. So that means 0 volts DC equals 32 degrees Fahrenheit and 10 volts DC equals 212 degrees Fahrenheit. In this PID loop, we're going to be asked to set up the drive with a fixed internal set point of 85 degrees Fahrenheit. And we're also being asked to set up a sleep function in the drive. This prevents the drive from running at for prolonged periods of time at a very low frequency, output frequency. For this sleep function, if the drive's output frequency drops below 15 Hertz for at least 10 seconds, the drive will stop running the motor. And when the discharge water temperature or the feedback signal reaches 90 degrees Fahrenheit or greater, the drive will wake up out of sleep mode and start running the motor again. Now, I want you to take a second to think about how you'd program and wire up the drive, and I will reveal that information here in a second. You can pause the video if you need to. Okay, here you can see the actual only wiring change I made to the drive is I moved my 0 to 10 volt signal, which was connected on AI1 and A ground on terminals 2 and 3. I moved that down to terminals 5 and 6, and that's because analog input 2 by default is partially already set up in the drive as a PID feedback signal. So all we did right now is just move the wiring. The run stop and vibration safety switch, those stay the same, as those functions haven't changed. Let's now program the first part of Lab 2 into the drive. Now we want to program in the 0 to 10 volt feedback signal, the feedback range to be 32 to 212 degrees Fahrenheit, and the fixed set point of 85 degrees Fahrenheit. Now, something that was not on the previous slide, but is very important, is that we make sure we set up the drive's PID loop so that the drive's output frequency increases when the feedback signal is greater than set point. This is actually opposite logic, for example, for a booster pump. So this is important to always make sure you set up in a VFD when you're commissioning a PID loop. So if you want to take time to pause the video here and attempt to program the drive yourself, please do so, and then unpause it and you can watch me program the drive. All right, so we're going to start by going to Menu, Primary Settings, and we're going to navigate down to an option called PID Control. I'm going to select that. Now there's two options to program the first part of this Lab 2. You could use the PID Assistant, or you could select this checkbox and enter in the data down below. I kind of think of this as like a folder structure with plain English text. I like using the folder structure below, so that's what I'm going to use. So I'm going to start by first selecting the checkbox here. And now I'm going to go down, activate PID control from. This is always active. Our PID will always be active, so let's leave that always active. Start-stop direction. Here we need to tell the drive where's the start-stop command coming from in PID mode. So here, even though we had set it up for speed mode to DI1, it was default. In PID control mode, it's not automatically selected. So here we need to select DI1 for our start-stop command. Our units, they're degrees Fahrenheit. That's by default, so we don't have to make any adjustment there. PID status, that's just a read-only. Now the feedback, okay? Let's set up the feedback signal here. Okay, this is the actual feedback. Right now we have 0 signal coming into the drive. The source, AI2, yes, that's where we have our feedback signal connected to, analog input 2. But now what we need to do is adjust the scaling. So here we go to select scaling. Our range is 0 to 10 volts. That's already correct. But the scale range, we need to adjust that because we're not 0, we're 32 degrees Fahrenheit. So we select edit and go to 3, 2. Then the maximum is 212. So here we're going to adjust this. Okay, now we have this adjusted. Go back. We go back. The set point. Our set point is 85 degrees. The drive is defaulted at 75 degrees. So here we need to make an adjustment. So the default is a constant set point, a fixed set point at all times. So that's already defaulted. So we just have to adjust the actual value of it from 75 to 85. Now, tuning, we're not going to do that right now. Down here, this is the last bullet point. Increase output, feedback is greater than set point. The ACH580 drive defaults so that for a cooling tower application. So when the feedback signal, let's say, for example, reaches 90 degrees Fahrenheit, that is greater than 85 degrees Fahrenheit. So the drive will increase and attempt to run the motor faster and faster, attempting to cool the water for a cooling tower application. If you had a booster pump application, you would actually select feedback is less than set point, like for a domestic booster pump for potable water in a building, for example. But we'll leave that at default, and that completes the setup for the first part of Lab 2. Now for the second part of Lab 2, we need to set the drive to go into a sleep mode if the output frequency falls below 15 Hertz for at least 10 seconds. The 10 seconds delay there is just to create a little bit of a buffer, so in case the output frequency in the PID control briefly falls below 15 Hertz, but then goes maybe back up to 18 Hertz because the more cooling is needed, we don't go into sleep instantly. We also need to set up the drive to wake up if the discharge temperature of the water from the tower reaches 90 degrees Fahrenheit. Now, if you want to pause the video here and attempt to do this on your own, do so now, and then unpause it, and I'll show you how to do it. All right. So in the PID control part of primary settings, 2 more down after we discussed previously the increased output over feedback greater than set point discussion, is sleep function. So we select sleep function here, and we're going to activate it by selecting it. Now, our activation level by default is 25 Hertz. We're being asked to set it to 15, so we'll quickly edit that to 15. And the delay time is 60 seconds. Here, we're going to edit this and make this 10 seconds. Now, boost time, we're not being asked to set that up, so we'll ignore that. Now, wake up deviation down here. Wake up deviation by default is 0 degrees Fahrenheit. Okay, so that means as soon as the temperature goes back above, for example, 85, if we left this at 0, if it went up to 85.1 degrees Fahrenheit, the drive's going to immediately exit sleep mode. We want a little bit of a delay there, so we want to let the temperature go up to 90 degrees Fahrenheit. Now to do this, because it's a deviation, we have to do a little bit of math here. So 90 degrees Fahrenheit is when we want to wake up from sleep mode. 85 is our set point. So 90 minus 85 is 5 degrees Fahrenheit. So the 5 degrees Fahrenheit is what we need to enter into the deviation here. And by default, we're not being asked to adjust this, but the wake up delay is half a second. This is kind of like the same concept of going into sleep mode. We waited 10 seconds. Here, we could delay, we're going to delay half a second if we reach 90 degrees Fahrenheit before we start running the motor. And we're just going to leave that alone because we're not being asked to change that. So this now completes Lab 2. For reference, here in Lab 2, for the first part of it, here are the newly added parameters to the modified parameter list in the drive. And also for reference, here are some screenshots where you saw me make adjustments in the drive. Here for reference are the adjustments in the drive to set up the drive for sleep mode. Moving on to Lab 3. The configuration request for this lab is asking us to adjust the acceleration and deceleration times both to 60 seconds. We're also being asked to adjust the PID control gain to 1.0 and adjust the PID control integration time to 270 seconds. In this lab, there is no adjustments to the control wiring on the drive. Let's now start by adjusting the acceleration and deceleration times to 60 seconds. If you'd like to pause this video and practice yourself before I show you how to do it, please do so now. All right, like we've done in the past, I'm going to go to primary settings and I'm going to go down to ramps. And right here at the very top, I have my accel time and then my decel time. So I'm going to adjust each of these from 30 seconds, the default setting, to 60 seconds. All right, and now that completes the first part of Lab 3. For the second part of Lab 3, we're now going to adjust the gain and integration time in the PID control loop. I'll give you a second here. Pause the video if you'd like to practice this on your own and unpause it when you're ready. All right, let me show you how to do this. So the fastest way I like to do it is go to primary settings, back to PID control where we were in Lab 2. And if you scroll down, there's an option called tuning. We'll select tuning. And you can see here the second and third one down, gain and integration time. Now the gain by default is 1.0, so we don't need to make any adjustments for the gain for this Lab 3, but we do have to adjust the integration time from 10 seconds all the way up to 270 seconds. The reason we're going all the way up to 270 is because this is a cooling tower, and cooling towers, the water temperature tends to change quite slowly. So we don't want the drive to start accelerating and decelerating the motor very quickly. We want it to have slow accel and decel so the water temperature is more stable. And this now completes Lab 3. Here's a list of the 3 parameters in Lab 3 that were added to the modified parameter list. For Lab 4, we're being asked to set up the drive for BACnet MS network so the drive can be monitored over the network. Now, when we're being asked to set up the drive for BACnet MS we have to be given 3 pieces of data from the controls contractor. The first is the baud rate, which in this situation is 76.8. The MAC address is 30, and the object instance ID number we're being asked to set up the drive for is 1030. Now, where would we land any MSTP wires from the controls contractor on the drive? If you selected at the very bottom down there on the X5 terminal block, the B+, A-, and D ground, that is correct. Now let's program the drive for BACnet MSTP for monitoring purposes only. Now if you want to pause the video and practice on your own, do so now. All right, I'm going to go back to primary settings. And if you scroll down the list, actually 2 under ramp where we set up previously accel decel times, there's an option called communication. We'll select this. And BACnet MSTP is considered embedded field bus. So we'll select embedded field bus. By default, it's off. And the selection, again, not selected. So we now have 2 options here. We have BACnet or Modbus. We're being asked to select BACnet. So we'll select save. And we will have to wait here a second while the drive does some initialization. All right. Now, station ID, that's the same as the MAC address. By default, it's 254. I'm going to edit it and make it 30. Now, by default, the baud rate is auto. Even though auto works, I'm just not a big fan of it. I like knowing the drive is set to the fixed baud rate on the network. A network is going to have one fixed baud rate, and I just like having it set to that value. So that's just my habit of tradition. And then the object instance number, that's also the device object ID. By default, that's a very large number, up there at 4 million and change. So we got to crank this all the way down to 1,000 here. So all right. Now, once this is done, you have two options. You could power cycle the drive, do a complete power cycle, and that will set up the drive when it reboots up so the BACnet is functional. Or you can scroll down to the bottom and apply settings, and then you don't have to turn on and off the main power to the drive. All right, and this now completes the programming for Lab 4. Here for reference are the newly added parameters to the modified parameter list after we set up the drive to be monitored over BACnet. For Lab 5, let's imagine that our cooling tower is a closed loop or fluid cooler style tower that has a spray pump to provide additional cooling if the temperature leaving the tower gets too warm. In this example, we're being asked to set up the drive to trigger the spray pump if the water temperature leaving the tower exceeds 95 degrees Fahrenheit. Now, if you say that 95 degrees Fahrenheit isn't realistic, just go with it in this example, please. Now, one of the key items is we do not want to trigger the spray pump if the drive is in an off state. Just because the temperature in the pipe or the water may be 95 degrees Fahrenheit or hotter, we don't want the spray pump activating if the drive's not running the motor. So we have to have two conditions. The drive's running the motor and the temperature exceeds 95 degrees Fahrenheit. Now, since we're using, we need to trigger the spray pump to run, we're probably going to have to use output signals on the drive. So I want you to think about this for a second. You can pause the video. And where would you wire up, or what would you do to activate the spray pump so it only runs when the temperature exceeds 95 degrees Fahrenheit and the drive is running? All right, you can see the wiring adjustments I made on the right. On the right, in the orange terminal blocks, those are the Form C relays. The drive has three Form C relays. I'm using two of them. The first one I'm going to set up as a supervisory, and we're using the Form A side of both relays. And the second one we're going to set up for running. So the supervisor will set up so in the drive, so when the temperature reaches 95 degrees Fahrenheit, that relay triggers, and the second relay will set up for running, and that makes sure that when the drive is running, that relay closes. And what we're going to do is I'm going to put a jumper wire between the two relays. So basically, we're putting these two Form C relays in series with each other. So both have to be satisfied for power to be sent to the spray pump for it to run. Now for Lab 5, we're going to program the drive for the supervisory function. Now, if you want to pause the video here and attempt it yourself, feel free to, and I'll show you how to do it. All right, we're going to go back to primary settings, our old stomping ground here. And at the very bottom of the list, I'm telling you was where it's located. So I'm going to go up and over the top to get to it faster. There's something called advanced functions here. All right, and we're going to go down to supervision and use supervision 1. That's disabled by default, so we're going to enable it. And we're going to set it to high. Okay, when the temperature goes high, we want this supervisory to activate. We now need to set up the signal. What is the supervisory operating off of? It's not operating off of the output frequency, which is default. It's instead operating off of the PID feedback signal, or PID feedback actual. Okay? And the last item we need to adjust is what is the temperature at which the supervisory triggers. We're going to adjust the high limit here. Recall, it was 95 degrees Fahrenheit. So this completes the first part of Lab 5, where we're just setting up the supervisory in the drive to trigger off of the feedback signal when it exceeds 95 degrees Fahrenheit. Now, something that was not in the initial configuration request, but we do need to implement is something called hysteresis. Hysteresis is basically creating a dead band around the set point that we want to turn on and off our spray pump. By default, the spray pump is going to turn on at 95.01 degrees Fahrenheit and turn off at 94.99 degrees Fahrenheit. This can create a lot of short cycling that could damage the starting contactor and or also the spray pump itself. So to prevent this, we want to enter in a value in the hysteresis here. Now the way the hysteresis works is the value you enter here is divided by 2, and then that value that's divided by 2 is added to, in this case, the high limit, and also subtracted from the high limit. So for example, if I put a hysteresis in here of 2.00, I now have the spray pump turning on at 96 degrees Fahrenheit and turning off at 94 degrees Fahrenheit. So this is just something to think about when you work with supervisories, is entering in basically a hysteresis to create a dead band around the actual turn on and turn off to prevent short cycling of the application. For the second part of Lab 5, we need to record the functional settings of the two relay outputs that are wired in series with one another so that the spray pump only activates when the drive is running and the supervisory is satisfied. Now, if you want to pause the video here, do so now, and I'll show you how to program it if you want to attempt to program it on your own. All right. Now, normally I'd say let's start at primary settings like we've done for the rest of the previous labs, but unfortunately, relay output adjustments can't be made under primary settings. So instead, we have to go to parameters at the very bottom of the list here. We have to go to complete list. And if we go down to group 10, this is where the relay outputs functional settings are adjusted. Now, parameter 10.24 controls the functional setting of relay output 1. By default, it's set to damper control. So we need to edit this. And I can tell you that the fastest way is to go up, and we go to supervisory 1. That's what we set up to monitor the output temperature of the tower. So we'll save that. And now the second relay that's wired in series is relay output 2. Parameter 10.27 controls the function of relay output 2. Now, that is by default running, so we do not need to adjust that parameter at all. This completes the programming for Lab 5. Here for reference are the newly added parameters to the modified parameter list in Lab 5 and screenshots where I made adjustments to the settings. For Lab 6, we're now being asked to change the name of the drive that appears on the top middle of the screen, which defaults to ACH580, to instead say Cooling Tower 2. Now, if you want to pause the video here, please do so now if you want to practice doing this on your own, and I'll show you how to do it. All right, so to do this, we are going to be able to do this in primary settings. So we'll go to primary settings, and at the very bottom of the list, I'm going to go hit the up arrow to get to it faster. Second one from the bottom, clock region display. We'll select that. I'm going to go down to drive name, edit. Now, the back arrow key here deletes what is currently on the screen. And then using The up arrow keys here, you'll be able to see how I'm going to go to the capital letters. And then using the down arrow key now, I'm going to go to C and go backwards up to T. And here you got to go over these arrows again and to select the symbols. Now this is easier if you were to hook up the drive to Drive Composer, for example. You just use your computer keyboard, and you could do this much faster than this method here on the keypad with just up-down arrow keys. So put a dash in, and then we need number 2. So there you go. So then you just hit save. And now you can see on the top of the screen, it says Cooling Tower or CT-2. So this completes Lab 6. Now before we finish up this lab, I want to mention one important thing. Since we set up this drive to operate in a PI or PID control loop to control the speed of the motor based off of a feedback temperature and then control the speed against a set point, how do we see that information on the control panel screen? Because as default, we see we have output frequency, motor current, and the voltage value on analog input 1. So how do we see what our set point is or feedback signal is? If we just hit the left arrow key here one time, we see we have pre-set up the Process PID set point on top, the feedback information that's off connected to analog input 2 on the drive, and then on the bottom, what our output frequency is at any moment in time. So it's just an important thing to note. Hit the left arrow key once from the home screen, and you'll get the PID process information. Thank you for following along on how to set up an ACH580 drive to operate a cooling tower. If you have any further questions, please reach out to your local ABB representative.